Hi, my name is Tim Fake. I would like to welcome you to my talk on Hacking a Bird, Satellite Hacking Part 1. I'm an application security consultant with Optiv Security. My main interest in the hacking world is RF hacking. I've been a licensed amateur radio operator for 26 years, recently upgrading to the extra class license. I've now started studying for my commercial general operator license with radar endorsement. I love space and have been studying satellites and satellite engineering since I became an amateur radio operator and was introduced to amateur satellites. Before I begin, I would like to mention where I got most of my pictures in this presentation from. Unless otherwise specified, most pictures in this presentation were taken from Wikimedia or NASA or they were created by me. If you want a complete list of references, contact me at one of the email addresses given at the end of this presentation. This presentation is part 1 of a series on satellite hacking. My hope is that the series will be a useful guide for anyone interested in the penetration testing of satellites. In this presentation, I'm going to cover 7 things. First, I want to cover why it's important to test the security of satellites. Next, I want to present a case that demonstrates what can go wrong if satellites are left vulnerable. In this case, I will discuss the ViaSAT Ukraine hack. Third, I want to talk about the skill sets that both overlap with more familiar penetration testing arenas and those skills which are unique to satellite penetration testing, interweaving a discussion on the anatomy of a satellite system. Fourth, I want to talk about the attack surface of a satellite system. And finally, I want to discuss what I plan to cover in future parts of this series. To give some perspective on the growing space landscape, according to NASA, there were approximately 800 man-made satellites orbiting the Earth in 2008. Today, according to the United Nations Office for Outer Space Affairs Online Index of Objects Launched into Outer Space, there are now 9,716 satellites. That is over 12 times as many satellites as there were in 2008. There are some estimates that by 2030, there will be 100,000 satellites orbiting the Earth, over 10 times as many as there are today. These satellites are used in a variety of ways, including communication, navigation, Earth observation, and research and development. Our daily lives are impacted tremendously by satellites. The most obvious is entertainment, through both satellite television, satellite radio, and through broadband internet. According to Euroconsult, a strategic consulting service, over 43 million people were connected via satellite to broadband internet service. As we drive towards universal broadband access, the number is expected to grow to 110 million by 2029. In addition to television and internet, our daily lives depend upon satellites in other ways. Some of them surprising. For example, satellites are important for economic transactions. ATMs, for instance, not only have GPS trackers in them in case of theft, they also use GPS satellite networks as precise clocks to timestamp all transactions from the moment you insert your ATM card to the moment you remove it and retrieve your money. Satellites are also used for weather forecasting, ship-to-shore communication, and airplane-to-flight control communication. If there's one thing that these statistics make clear, satellites are part of our critical infrastructure. As a result, they need to be protected. That protection can't happen without the use of penetration testing to make sure that vulnerabilities are found and patched before bad actors find and exploit them. That being said, let's look at one example of where a state actor took advantage of an unpatched appliance to compromise the satellite system. This attack not only took down internet for an entire country, but also severely compromised that country's military assets and served as a digital-first strike on that country's invasion. On February 24, 2022, thousands of modems and routers from the ViaSAT KASat satellite network that provided the military and general population of Ukraine with internet and communications access were infected with malware that wiped their firmware, rendering them inoperable. To better understand this attack, a closer look at what the ViaSAT KASat network is and how it functions will be helpful. In this brief diversion, important satellite terminology will be covered. The International Telecommunications Union, an agency under the United Nations, classifies satellite radio communications under 3 categories: fixed satellite service, FSS, intersatellite service, ISS, and Earth Exploration Satellite Service, EESS. FSS satellites communicate with specific locations on the Earth. ISS satellites are inter-satellite communications systems. EESS satellites are used to observe the Earth, for example, weather satellites and space satellites. The KA-SAT network is composed of a special type of FSS satellite called a high-throughput satellite, which means it can transfer data at a higher rate than standard FSS satellites. In this case, they can transfer data at 70 gigabits per second. The KA-SAT satellites are in geostationary or geosynchronous orbit. More on this when we talk about orbital mechanics. Satellites operate on bands designated by letters, which indicate their uplink and downlink frequencies. In the case of the KA-SAT satellites, the uplink and downlink frequencies are in the Ka band. Uplink frequencies are between 26 and 40 gigahertz, and the downlink frequencies are between 18.8 and 19.3 gigahertz. Most satellites communicate using an architecture known as a bent pipe architecture, the KA-SAT satellites being no exception. This simply means that the signal that is transmitted up to the satellite is then turned around without any processing and sent back down to the receiving station. Satellite networks are composed of three segments: the space segment, the ground segment, and the user segment. I will talk about these segments more later. The space segment is composed of the satellites themselves. The ground segment is composed of the launching platform, ground station, control center, remote terminals, and integration and testing facilities. The KA-SAT ground segment consists of 10 gateway Earth stations that are interconnected by fiber links and connected to the internet. These stations control a satellite antenna spot beam array. This array allows the satellite to offer its services over a limited area, in this case, Ukraine. The user segment consists of all the customer terminals used to interact with the services offered by the satellite. In the case of the ViaSAT KA-SAT system, that includes all the modems and routers scattered across Ukraine. Now that an understanding of the KA-SAT system has been established, we can circle back to the attack. The KA-SAT hack began at the ground segment level. At the time of the attack, the ground segment was being managed by a third party called Skylogic. Skylogic used FortiGate VPN appliances manufactured by Fortinet to access their control servers, gateway Earth stations, and Surfbeam 2 modems. In 2021, Fortinet notified its users of a breach that leveraged an unpatched vulnerability, CVE number 2018-133779. Found in 2018 that permitted the attackers to download credentials that would permit access to 87,000 FortiGate SSL VPN certain devices. At the time, Fortinet released a patch for this vulnerability. Later in 2021, the Russian hacker group called Groove published credentials for over 500,000 FortiGate SSL VPNs. Skylogic hadn't patched this vulnerability in their FortiGate VPNs, which were used to connect to the ground segment. It's assumed that the attacker leveraged this unpatched vulnerability to access the gateway Earth station over the internet. The attacker was then able to target a specific area thanks to their ability to control the spot beam array and beam malware called Acid Rain that targeted MIPS systems. The malware wiped the firmware from the user segment routers and modems, causing region-wide communication and internet outages. From the above discussion, we can start to see where the skill sets used for attacking web applications and networks overlap with the skill set used for hacking satellites. In the ViaSAT hack, the attackers went after the ground segment, which had known vulnerabilities in its VPN. Appliances that could be accessed via the internet and connected to the gateway Earth stations. We can also imagine scenarios where the attacker has access to the user segment for a specific service that might have a vulnerable web application that can be manipulated to send erroneous commands to the ground segment, which may result in denial of service. These types of attacks are par for the course in the standard penetration testing attack scenarios. All of these attacks are noisy, and that if logging and alerts are set up properly, they will probably be discovered pretty quickly. Things get interesting when we shift from attacks against the ground and user segments to the space segment. The thing that I find most interesting about the space segment is that attacks can occur more covertly than they could at the ground and user segments. An attacker who is mainly interested in only gathering intelligence and sniffing data can do this anonymously at the space segment. At the ground segment, an attacker would need a foothold on the system before sniffing data. This would most likely be noisy and result in logs being generated. At the space segment, an attacker is only pulling down data through the air, which is available to everyone with the right knowledge, without the need to access any networks that may generate log entries. Given this open availability, one would expect that sensitive data would be encrypted, but that isn't always the case. One example of this is the Inmarsat satellite system. Inmarsat is a British telecommunications company that provides both voice and data over their satellite networks. As an aside, in 2022, ViaSAT purchased Inmarsat. Inmarsat voice is typically encrypted, although the encryption is weak. Inmarsat data, however, tends to travel in plain text, and anyone with a $25 SDR, a patch antenna, and decoding software can intercept these transmissions. So you ask, what unique skills do I need to hack satellites? These skills fall into two categories: tracking satellites and RF engineering. The first category includes orbital mechanics. The second category includes digital signal processing and signal analysis, RF propagation, and specialized hardware and software. If you're really interested in satellite hacking and want to become more familiar with the hardware end of things and of propagation and RF hacking in general, and you haven't done so yet, I highly recommend getting your amateur radio license. This gives you the opportunity to experiment with working amateur radio satellites so you can get an idea of how satellites work. First topic I want to cover is orbital mechanics. This skill set is probably one of the most unique for hackers and can be quite a deep rabbit hole. Although this set of skills is broad, for our purposes, its primary importance revolves around being able to track satellites in orbit, so that we know where to point our antennas. There are plenty of websites and software packages out there that give us enough satellite tracking information to be able to point our antennas in the proper place. But since part of our job as a hacker is to perform reconnaissance on our targets, it would be helpful to know a few terms and have at least a basic understanding of satellite orbits. At the bare minimum, you should know the difference between geostationary and geosynchronous orbits. A geosynchronous orbit is one in which the object in orbit is locked into motion with the Earth. This orbit can be any inclination. Geostationary orbit is a specific instance of geosynchronous orbit, which is locked in motion with the Earth at the equatorial plane. Geosynchronous and geostationary orbits are prograde, which means that they move the same direction as the Earth. The other term of art here is retrograde, which means that the motion of the object is the opposite of the Earth or other planetary body. There are a few other orbits that you might come across during your target reconnaissance. Low Earth orbit is around 160 kilometers to 1,000 kilometers above the Earth's surface. Since the orbit is lower in altitude, it costs less money to place an object there than it does in geostationary orbit. As a result, most man-made objects are found there. An example satellite in this orbit that you may have heard of when researching satellite hacking is the Iridium satellite system. However, the downside to this type of orbit is that it has a lower field of view, which means that the signal can only cover a small section of the Earth's surface. As a result, most communications, broadcast, and GPS satellites find themselves in geostationary orbit. You might also find satellites in medium Earth orbit. As the name suggests, this orbit is found between 1,000 kilometers, between the 1,000 kilometer low Earth orbit limit and the start of the geosynchronous orbit, which starts at the altitude of 35,786 kilometers above the Earth's surface. As an important aside to keep in mind, when you read research and technical articles on satellite orbits, you will frequently see that the altitude stated in kilometers above the radius of the center of the Earth and not above the Earth's surface. Most calculations are performed using the former number and not the latter. You might also hear about polar and sun-synchronous orbits. Polar orbits are low Earth orbits that travel over the polar regions, whereas the sun-synchronous orbits are special types of polar orbit, but rather than being synchronous with the Earth, they are synchronous with the Sun. One final thing to keep in mind regarding orbital mechanics is how the orbital motion of satellites are described mathematically. These orbital elements are called Keplerian elements, and they are based off of Kepler's three laws of planetary motion. As a review, Kepler's three laws are: 1. The planets orbit the Sun in an elliptical pattern, with the center of the Sun located at one focus of the ellipse. 2. If a line drawn from the center of the Sun to the center of the orbiting planetary body, that line will sweep out equal areas in equal periods of time. And finally, 3, if you take the ratio of the squares of the periods of any two planets, that ratio will be equal to the ratio of the cubes of the planet's average distance to the Sun. There are 6 Keplerian elements that describe the motion of a satellite: eccentricity, the length of the semi-major axis, inclination, longitude of the ascending node, argument of periapsis, and true anomaly at epoch. We'll go through each one of these and in order. The first one, eccentricity. Eccentricity is literally the shape of the orbit of the body. Eccentricity is a measure of how elongated the ellipse of the orbit is. In the case of geosynchronous orbit, mentioned earlier, the measure of eccentricity is 0, indicating that the orbit is a perfect circle. Number 2, the length of the semi-major axis is simply the measure of the distance between the center of the satellite and the center of the Earth. This is the size of the orbit. 3, inclination is simply the measure of the angle of the satellite's orbit with respect to the equatorial plane. 4, the longitude of the ascending node is the angle between the ascending node, which is the point at which an object passes from below a reference plane to above that reference plane, and the reference direction designated by the inertial or rotational x-axis through the Earth. You can think about the ascending node as the point at which a satellite goes from the southern hemisphere, ascending, to the northern hemisphere. Number 5, the argument of periapsis is the angle between the ascending node and the point at which the satellite is closest to the Earth, also called the periapsis. The true anomaly at epoch is its angle between the satellite's periapsis and its current position. Again, don't worry if this part was tough to follow. Although Keplerian elements are important, and they will help you when reading satellite documentation, there are plenty of applications available online that keep track of satellite orbits. If you're interested in learning more about orbital mechanics, I recommend a game called Kerbal Space Program. Next, I want to briefly go over RF engineering concepts that play a crucial role in satellite hacking. In the slides that follow, I'm going to briefly cover the following concepts. 1, RF propagation. 2, hardware. And under the hardware section, I'm going to cover software-defined radio. In software-defined radio, I want to cover digital signal processing, communications protocols, and signal analysis. Next, I want to cover antenna design. Finally, I want to cover some software. I want to cover GNU Radio, Universal Radio Hacker, SIGDigger, GQRX. Finally, in that section, I want to cover 2 Linux distributions that have a lot of the tools that I just described already installed. First up on our list is RF propagation. There are a few aspects to RF propagation that are important to satellite hacking. These areas are important because they affect how you receive the satellite transmission and how the satellite receives your transmission. The first of these is ionospheric refraction. Ionospheric refraction, as the name suggests, is the refraction or bending of radio waves by the ionosphere. Refraction can happen on both ends. Satellite signals may be bent back into space, or terrestrial signals intended for satellites may be bent back to Earth. This generally occurs more on the HF-VHF end of the radio spectrum, but can also have an impact on getting precise orbital positions of satellites on UHF. The process of tracing a radio signal through the atmosphere is called ray tracing. There are a number of open source tools available to assist in ray tracing, of which Opal is one. This problem should be taken into account when you do your satellite reconnaissance. Next area to consider is ionospheric absorption. The ionosphere can absorb both RF coming from your station and going to the satellite, and coming from the satellite and going to your station. Again, this happens more on the HF and VHF end, but still can happen on UHF and above. Software mentioned earlier can also help with modeling and compensating for issues that this may cause. Satellites travel around the Earth at considerable speeds, as compared to terrestrial objects, such as yourself. The signals from those satellites are also traveling at considerable speeds relative to your transceiver station. As a result, there is a shift in frequency, or wavelength, of the signal, which is called Doppler shift. You also need to compensate for this by tuning your antenna up or down in frequency. Finally, anyone who has ever had a satellite TV is familiar with rain fade. This occurs when rain, snow, or ice in the atmosphere absorbs RF. This is a major problem in frequencies above 11 GHz. To compensate for this, you can increase the power of transmission, but that doesn't help if you don't have access to satellite control. On your end, it's probably best to wait until the disturbance passes. Although there are older satellite transceivers out there that aren't software-defined radios, the most likely piece of equipment that you'll use when penetration testing satellites is an SDR. To understand what an SDR is, let's take a step back and look at the components of a standard transceiver. Standard transceiver is composed of an antenna, duplexer, low noise amplifier, preamplifier, voltage-controlled oscillator, mixers, a phase-locked loop control system, high-pass and low-pass filters, in-phase quadriphase filters, analog to digital converters, and digital to analog converters. In an SDR, most of these physical components are implemented in software. SDRs make an excellent platform for performing satellite penetration testing, due in large part to the field programmable gate array that sits at the heart of the device. Most of the physical components of the radio described earlier are implemented with the FPGA. In addition to those components, the satellite penetration tester can use the software like GNU Radio to create modulators and demodulators for the various protocols that they might encounter during an engagement. Another equally important component to an SDR is the digital signal processing chip. The digital signal processing chip and the digital signal processing that it performs in the SDR is another deep rabbit hole which deserves its own talk. Here I hope to give you some basic understanding of a couple of the fascinating topics that are covered in this exciting field and how they apply to satellite hacking. The first topic I would like to cover in this section is the fast Fourier transform. This topic alone can take up an entire year-long engineering course. The best way I have seen FFT explained in a simplified way was on the Better Explained website. You can think of the FFT algorithm as a filter that can extract information, in this case the frequencies by which the waveform is composed, about a waveform. A waveform can be thought of as a smoothie, with its ingredients being frequencies. If you wanted to extract the ingredients, you would need filters for each ingredient. If you want to extract the ingredients from an orange banana smoothie, you would need filters for orange, banana, sugar, milk, and water. For our waveform, the FFT behaves as though it has all of these filters needed to separate the waveform into its frequency components. When you hear anyone talk about how FFTs convert signals from the time domain to the frequency domain, all they mean is that they have taken a waveform over time and used the FFT algorithm to extract the individual frequency components. Here we can see this transformation of what the FFT does to a signal when it transforms it from the time domain to the frequency domain. In the beginning, we see what looks like a square wave with ripples on top. We then see then we see the individual frequency components being extended behind the square wave. Finally, we see a frequency domain graph showing the frequency composition of the original waveform. A short discussion of SDR and DSP wouldn't be complete without discussing IQ. Whenever we or satellites transmit a signal, we are taking our audio or digital frequency, also called the baseband, and combining it with something called the carrier wave. Carrier wave has more energy than the original signal, so therefore it can travel further. This process of mixing is called modulation. The carrier wave is a pure sine wave. Modulated sine wave can be broken down into two amplitude modulated waves called in phase, or I, and quadriphase, or Q. Quadriphase is separate from the in phase sine wave by a 90 degree phase shift. In this figure, we have a sine wave that has been separated into its in phase, blue, and quadriphase, red components. One of the cool things about a sine wave is its relationship to the unit circle. I and Q are typically plotted on what is called the imaginary plane. The I component is plotted in the X, or real axis, and the Q component is plotted on the Y, or imaginary axis. In the diagram on the left, we can see the relationship between the I and Q components, and the sine wave circle relationship in what is called the phasor diagram. On the right, we can see the in-phase sine wave, quadrature sine wave, and resultant waveform adding both together. The equation below the figure gives the relationship between the frequency f and the phase shift, where phi is the phase shift in degrees, 360 degrees is the total number of degrees in a circle, and delta t, which is the change in time of the amount of time that has elapsed. Given this information, we can see that a rapidly changing phase shift, phi, as shown in the figure, results in the frequency modulation, f. Why is this important for SDRs? As mentioned above, our baseband is the audio or digital information with the carrier signal removed, so that means that the baseband contains all the important information that we want to analyze when working satellites. When we separate our baseband into I and Q, it makes our signal easier to analyze. To further see the importance of IQ signals, let's turn our attention to signal analysis. First thing that we need to do when analyzing a signal is to determine the modulation type. To understand why modulation is used and how to determine the modulation type, a quick diversion into how signals are transmitted wirelessly will be helpful. In order to send a message wirelessly, we need to transmit that signal using an antenna. The size of the antenna is determined by the wavelength of the transmitted signal. The wavelength of a radio wave, lambda, as seen in bullet point 1, is equal to the speed of light in a vacuum divided by the frequency. As this equation suggests, the lower the frequency, the larger the antenna. This poses a significant problem if we want to transmit, for example, telephone quality voice, which is on the order of 200 to 3000 hertz. For frequencies in this range, the antenna would have to be between 100 kilometers to 1500 kilometers in length. This is one of the reasons why we mix a signal with carrier wave mentioned earlier. This is the concept of modulation that I mentioned before. In number 2, we see an equation representing the sine wave's most basic form as a function of time. The symbol A represents the amplitude of the sine wave, its deviation from 0. 2 pi represents the angular velocity. Think about what you saw earlier in the phasor diagram showing the vector coming out from the origin and rotating around the unit circle. The angular velocity is how fast the vector rotates. F is the frequency and phi is the phase or how much the sine wave shifts to the left or right. In these components, the amplitude, frequency, or phase represent the ways in which signals can be modulated. There are 2 families of modulation techniques, analog modulation and digital modulation. The first analog modulation type that I want to discuss, shown here, is amplitude modulation. The top waveform in the picture is the baseband. Second waveform is a carrier wave, and the third shows the carrier wave being amplitude modulated by the baseband. The 2 things to notice about this waveform are, 1, that as the name suggests, the amplitude, the distance between the zero center line and the peak of the wave, of the carrier wave is being modulated by the baseband, and 2, the envelope shown in the last waveform, which is created by the low frequency components of the baseband and is important when demodulating the signal, which is done with an envelope detector, one implementation of which uses the FFT discussed earlier. The second of the 3 types of analog modulation types is frequency modulation. Here, the baseband signal is on top and the carrier signal under it. On the right is the resulting modulated signal. Notice in this case that the amplitude plotted in the y-axis is stable, but this time the frequency, the number of waves per second in hertz, is changing. The third type of analog modulation is phase modulation. As you can see, phase modulation looks very similar to frequency modulation and is very difficult to tell apart without some knowledge of how the signal was modulated. In fact, phase modulation can be used to create frequency modulation by constantly varying the phase shift. So what is this phase modulation, you ask? Well, imagine a waveform being plotted with the x-axis representing time and y-axis representing amplitude in volts. If we take an instantaneous amplitude of plus 1 volt and shift it so that the amplitude is now minus 1 volt, that represents a phase shift of 180 degrees. We can use the baseband of a signal to modify the phase of a carrier wave in just such a way. If we constantly change the way the baseband shifts the phase, for example, at one point the baseband might shift the carrier by 180 degrees, and at some future point it might shift it by 90 degrees. The phase modulation results in a frequency modulation. Each of the basic analog modulation types described above have their digital equivalents. The first of these I want to discuss is amplitude shift keying. Figure A shows the data baseband. Figure B is the carrier wave that the baseband is going to modulate. Figure C shows one of the simplest forms of amplitude shift keying, or ASK, called on-off keying, or OOK. In OOK, the carrier wave is only turned on when the baseband bit is 1, in the case of in positive logic. In the case of this figure, the carrier wave is a sine wave that oscillates between +1 and -1 volts, when the bit is 1 in the baseband, and when the bit is 1 in the baseband. Figure D shows a standard ASK, where the carrier signal oscillates between +1 and -1 volts amplitude when the baseband bit is 1, and drops to plus or minus 0.5 volts when the baseband bit is 0. The second digital modulation type that I want to discuss is frequency shift keying. In this figure, we can see that the amplitude stays the same over time, but the frequency shifts based on whether the bit is either 0 or 1, which can be seen on the top of the figure. The last digital modulation type that I want to cover is phase shift keying. Here we see a shift in the phase of the waveform based on whether the bit is 0 or 1. The bits can be seen on the top of the figure, and if you look at the separating line between the bits, you can see that there is a phase shift to the waveform. There are many more digital modulation types that are more complicated than those that I just went over. One that you might run across at some point is quadrature phase shift keying and quadrature amplitude keying. Both of these are used in Wi-Fi signals and are worth an entire talk, but I wanted to briefly mention them here. Next, I want to briefly touch on some well-known software tools and a couple of Linux distributions that you can use on your journey into satellite hacking. The four software tools that I want to discuss are GNU Radio, Universal Radio Hacker, SIGDicker, and GQRX. The king of all SDR hacking software is GNU Radio. The main application is command line based, but the GUI shown here is what is typically used. Users create flow graphs that represent transmitters, receivers, and all the DSP components that are needed to process information coming from an SDR. Once the flow graph is complete, the user presses the play button. The flow graph is converted into Python code and then run. The user doesn't have to use the GNU Radio Companion GUI, however. They could instead write their entire flow graph in Python using GNU Radio's extensive API. Although GNU Radio can do everything that the next two applications can, it takes a little more effort as you'll have to build everything from scratch, whereas the next two applications, all implemented with GNU Radio, have many useful signal analysis features built in. The second tool that I have found to be incredibly useful when doing signal analysis is Universal Radio Hacker. This tool gives you the ability to either record a signal or import a signal that has been recorded from another application and perform automated analyses on it to retrieve the bit stream. In addition, it allows you to replay either the original bit stream or modify the bit stream and replay it to perform replay attacks. The next tool I want to cover is SIGDicker. Much like with Universal Radio Hacker, signals can be recorded or imported and further analyses can be performed to determine the modulation type and extract the data bit stream. One of the unique features that this has is the ability to compensate for Doppler shift in the signal, which is what I mentioned earlier. The final tool I want to cover is called GQRX. Although this tool does not fit in with the other tools in that it doesn't provide an easy way to do signal analysis, it gives the person an ability to view the complete spectrum and scan a bunch of signals based on a list of frequencies. This tool is really useful if you want to scan the frequencies for interesting signals. In addition, you can set it up as a server that can scan a list of frequencies and send them over a network through TCP or UDP. One possible satellite hacking use case for this would be if you had a list of frequencies that might be used for a satellite and you want to move a satellite antenna to see what frequencies are active in a given area of the sky. Some of the applications listed above can be challenging to install on some versions of Linux. That being said, I wanted to touch briefly on two Linux distributions that already have these applications installed. The first one is Dragon OS. This distribution has most of what you need to get started in satellite hacking and RF hacking in general. It has versions for both the x86-64 series of processors, as well as the ARM processor that is used in the Raspberry Pi, in case you want to set up a mobile rig. The second Linux distribution is SIGINT-OS. This distribution is relatively new to the game and doesn't have nearly as much pre-installed as DragonOS does. Some of the notable applications that it does have installed are the IMSI catcher, LTE decoder, and GPS transmitter. When people think about satellite antennas, most think about the satellite dish as pictured on the left. Many people think that the large dish collector is necessary for satellite communication. The dish part is called the parabolic dish collector. This feature collects and reflects a satellite signal back towards the feed horn, which contains a signal down converter, called a low noise blanker or LNB, and a low noise amplifier or LNA. None of these are necessary components to an antenna system used for satellite work. The dish component provides additional gain to the signal, which can be useful, but not absolutely necessary. The figure on the right gives an idea of the different types of antennas available for satellite work. The bottom square boxes are two patch antennas. On the top are two right-handed circularly polarized L-band antennas. One of the most important things to remember when picking out an antenna or building your own is the type of polarization that the satellite uses when transmitting and receiving. Circular polarization can either be left-handed or right-handed. All of this information can be found on the internet for most satellites. This is a deep topic that deserves its own presentation. Before my digression into hacking skill sets needed for satellite hacking, I started talking about the anatomy of a satellite system, mainly focused on the ground segment. Now I'm going to turn to the space segment. Space segment is composed of 5 subsystems: attitude and orbit control, telemetry, tracking, command, and monitoring, power systems, communication, and antennas. Attitude and orbit control consists of the propellant tanks, thrusters, and motors, such as the liquid apogee motor shown here. Telemetry, tracking, command, and monitoring are actually spread across both the ground segment and the space segment. These systems provide satellite health information, satellite location, and other satellite telemetry. The power system includes the solar panels and the onboard batteries. The communication system is composed of several interconnected units called transponders. These transponders typically have their own low-noise amplifier, bandpass filters, and frequency up converters. There are 2 types of transponder units that can be used: bent pipe and baseband. The bent pipe transponder, mentioned during our discussion on the ViaSAT hack, uses an LNA to amplify a received signal and send that signal back to Earth. The baseband transponder, as the name suggests, converts a digital signal that contains both the carrier wave and the baseband wave, recall our conversation regarding baseband from earlier, to its baseband wave through digital signal processing and retransmits it back to Earth. This antenna subsystem on a satellite can be quite extensive. Each transponder may have its own group of antennas for each band that the satellite covers. In this picture, we can see antennas for S-band, Ku-band, and Ka-band. Also of note in this photo is the mention of the polarization types for each antenna that we discussed earlier. Finally, I want to briefly discuss the attack surface of a satellite. This is another deep topic that deserves an entire presentation. Let's start with the definition for an attack surface. According to NIST, an attack surface is the art of points on the boundary of a system, a system element or an environment where an attacker can try to enter, cause an effect on, or extract data from that system element, or environment. Given the definition, the attack surface of a satellite is quite extensive. For the space segment, every component of the communication and antenna array is an attack surface. When we include the ground and user segments, the attack surface gets much wider. The larger the attack surface, the more opportunity for an attacker to gain a foothold. Before I go, I want to mention some of the areas in which I want to create future presentations. First of all, since I covered very briefly the attack surface, I would like to do another whole video on just the attack surface of a satellite system. I also want to go into further detail on satellite antenna design. As I mentioned above, this is an important topic that satellite hackers should be familiar with. I also want to give people an introduction to using GNU Radio to communicate with satellites. Finally, I would like to be able to do a deep dive into satellite signal analysis. Thank you for your time. I hope you enjoyed this presentation and that it taught you something new. As I said, this is a new talk and I would love to hear comments from you about ways to improve it. If you have any questions at all or comments, you can reach me at one of these email addresses. Thank you.